welcome everyone who's joined. Nice to have you here. So today I was trying to try something new and do some community updates because it's been wild. There's been so much happening the last few days. It's hard to keep up for myself. So I will be trying to go through a few things that have been happening, which have been really interesting. So yeah, so this stream will be about the Nintendo Game & Watch, of course, and how to develop for it and stuff like that, how to back up. And I just want to start by going through what has been happening. So yeah, like a week ago or 2 weeks ago, we stacksmashing and I found a way to export or to download the internal flash and external flash from the unit without breaking the device and disabling the readout protection and putting it back. And since then, a lot of things have been happening. So I've been working on an emulator port for the Nintendo NES using the NoFriendo emulator. And yeah, so far it's only like a work in progress, but it's playable. The audio works, the video is good enough, but it's not perfect and so on. But it's still kind of fun. And then there's also a Game Boy port in the works. I've merged the changes from stacksmashing, trying to make it work in the same project structure so that we don't have multiple projects and so on. Because being able to have one repository with the multiple emulators makes it kind of neat to, like it opens the possibility to actually have multiple emulators running at the same time, or like that you can switch them on from the same binary. So there's like a reason to keep it in the same repository. Yeah, and then after we released the backup tool, there has been a lot of response, and lots of people have been joining the Discord and asking questions and so on. It's been hard to keep up, but it's been really fun. So I just want to say thank you to everyone who's been sending pull requests, because there's been quite a lot. So thanks a lot for that. Yeah, so I've opened up a few tabs here with stuff that I want to show. So first of all, yesterday, there were a few X-ray images coming in on Twitter. Very, very cool. So maybe you think, okay, X-ray, that looks cool, but why? What is it for? Well, the reason is that you can trace out the traces where all the electrical paths go, and that way you get a full net list on how everything is tied together. And the reason why you want that is in order to be able to understand everything, basically. So currently, we have a basic understanding of how stuff works. We have the LCD working, we have the audio working, we have the buttons working, but the details about the power supply, about the charging and stuff like that is not fully understood yet. So that is really helpful. So here we have a few more. Really nice detail. And Daniel Cuthbert also took some really, really high resolution pictures. Like here you can see bubbles in the solder joints. Like, wow, that's amazing. And you can also see the 3D structure of the vias here. It's really, really cool stuff. So using these images and increasing contrast and so on, you should be able to trace out all the paths. And let's see here if I can find this. Right. So just yesterday, someone called Jake sent an issue with some text explaining that he had traced out a lot already, and also tried to figure out what all the components are and how they are tied together. Really, really amazing stuff. So I hope that we can reuse this and make like a full trace, complete trace of everything eventually. If we just combine all of our efforts, and we should be able to understand how it works. So it's really, really cool stuff. And to find this, you can go to the Game & Watch base project and go to the issues, and it's the issue number 1. And there you will find all of this. And he made a repository with his efforts. I think the goal seems to be to have like a KiCad project to with all the components and how they are connected together and so on, which will be extremely helpful. Really, really cool stuff. And let me see if... Okay. I'm really bad at keeping up with the chat, sorry. So let me see here if I missed something. Hey, Mattis here. Yeah, nice to see her. I'm interested on MCU pins. One is used by LCD, but I can leave. Another, I don't know. Maybe with help from this X-ray. Yeah. Oh, yeah. So let me show you that as well. Let's go to the hacking repository. So this is the first repository with the initial XR tools, but there is a wiki here as well. It's maybe we should have a link to this on the main site, because here you have some information about the buttons and so on. So this is, we've collected this information, which, yeah, I mean, it's helpful, but it's not complete. That's the thing. It's it doesn't really explain how stuff is connected, like if there is a MOSFET and how that MOSFET is driven and so on. So, I mean, this is super helpful, but hopefully we will be able to understand how everything works in detail. So currently we have a bit of a worrisome issue where if you power on during power on and you turn on some GPIOs in a certain time with a certain timing, you might get strange voltages on the VCC, which is not very nice. So we're working on that, trying to find a good way to be sure that it's always safe voltages. But I mean, all of this is it's homebrew. If you run non-Nintendo code on your device, you're on your own. Of course, we don't release stuff that we know is broken, but at least we try. We do our best. But of course, with custom firmware, anything can happen. So just remember that before you try stuff. All right, so that was about that. And then, yeah, right. So Stelnia has been working on some really cool CAD stuff, like a complete case reproduction. So that is really amazing. It looks great. So you might think, why do we need this? Well, for one, you could essentially 3D print a second one. If you want to mod it, you can change stuff and print your own. But it's also really nice to have for when you make your own PCBs. You know, for example, exactly where you have areas that you need to keep out. And where if you have a component that is too high, it might hit one of these, I don't know the technical term, but yeah, extrusions or whatever. So that's really cool. And we have, on the Discord, we have chat room where we discuss replacement PCBs. So you may, 3D models are cheat sheets for dimensions, exactly. And when you put a 3D model of your PCB in that 3D model, you have everything. You can see that it fits. It's perfect. So you might wonder why do you need a replacement PCB? You just bought the unit. It has a microcontroller. It's awesome, right? Yeah, but if you put an FPGA here, you could theoretically be able to run a cycle accurate emulator because it implements the actual processor. So it runs in real time. There's no emulation. It is whatever you want to emulate. It becomes that. So I'm really excited about that because I've been thinking about making some FPGA game thing, but I've never really had the motivation to do so. And to be able to make a case and so on and fiddle around with screens and I don't really like to do that. But with this unit, we get all of that. We have the keys, we have the case, we have the LCD, we have backlight. All of that is already solved for us. So that's really nice. Yeah, so this is a work in progress sketch. Right now, we don't really know exactly what we want on it, but we're leaning towards a ECP5 FPGA. The reason why ECP5 is interesting is because there is a completely open source toolchain to generate bit streams for it. So you can have, yeah, essentially it makes it life becomes easier because your bit stream, you don't need to download like tens of gigabytes of proprietary tools, which you need with Xilinx, for example. Uh, it's much more streamlined, and also since the tools are just focused on one single FPGA, or like, yeah, they have targets, that makes them faster because they don't. I mean, they have one goal. So anyway, I'm not really good at explaining why it's good, but it is nice and it's open source. So if there is a bug, you can fix it, which is not the case with Xilinx and similar big vendors. Implementing the Odroid Go hardware for another PCB would also be cool. We should do both ECP5 and Odroid Go. Yeah, so exactly, we can do anything. So with these designs, once they are verified, we can share them, and multiple projects can run at the same time, of course. That would be really cool. So I'm really excited about this because, yeah, ECP5 is sort of, I like it a lot. But we also need some RAM. We haven't really decided exactly how that will work, but probably some SD-RAM. We'll see. All right. Yeah, right. So here I just opened a tab. So this project, I just learned about it. I haven't heard about it before, but it seems to be a collection of game platforms in FPGAs. So here's a good list of links for Gateware, for various consoles that, like, once you have some sort of source code for the Gateware, even if it's not designed for the FPGA we're using, we could port it. It opens up that possibility. Yeah. So that's pretty cool. And then there was this comment on YouTube by the author of No Friendo. So the emulator we're using on the emulator port, yeah, which is really cool. So that was kind of fun. What about run MicroPython on that Nintendo? Yeah, definitely, no problem. I don't have it ported yet, but yeah, exactly. Feel free to port it. That's the spirit. So the thing is that CircuitPython is really easy to port. MicroPython is basically the same STM32 series of microcontrollers have already been ported, so porting this specific one shouldn't be hard. Should be pretty straightforward. The biggest problem is that you don't have USB out of the box, and that makes it. Oh, you're working on it. That's nice. Cool. Good luck. And if you have any questions, just just write about it in the chat. Cool. Yeah, so the main drawback is probably that the USB data pins are not connected, so you don't get the nice MCU mass storage device thing where you can upload Python code easily. Because that's really what makes CircuitPython nice. Like, you just plug in USB and you can basically drag and drop Python files to the device and it will just run. It's really convenient. Yeah, and then this was also pretty cool. So Cyanic found out how to trigger the test mode. So there's a built-in test mode in the device, that shows, basically factory test. It's a hidden menu. I just wanted to show this because it's pretty cool. I've managed to reproduce it once. It's a little bit tricky because there's these times we need to do stuff, but it's kind of fun. Yeah, the MCU has USB pins. I want to wire them from the connector. Yeah, you can try that. So I tried that and didn't get it to work, but I blame myself because I probably made some mistake. But the biggest problem is that the USB pins are wired to the LCD as well. But maybe it will not be a problem. I'm really curious to hear your progress on that. Right, and then there was progress on the drawing song, trying to reverse engineer how that works. So I don't really remember the details, but essentially it's a GIF with without the header, I think. And if you want to check out the some reverse engineering efforts, you can go to this repository by James. I don't really know any details about it. I just wanted to show it. That was that. Yeah, so it turns out that OpenOCD, okay, let's hear, but MC has USB pins. Yeah, okay, so the tool that we released, Game & Watch Backup, we asked the user to install OpenOCD. The problem is that we need functionality in OpenOCD that is not included in the upstream released version in Ubuntu. So you need to either check it out and build it yourself, or download it from XPack, something I didn't know about either. So this seems to be like a secondary package manager. But I really wanted to make a deb file and have it installed the common way. So I made that. So this repository, it utilizes the GitHub workflows to run Docker to build a deb file with OpenOCD from Git, and then it publishes that to the repository. So you can use these lines in your console to download that deb file and install it in your system. And that will install OpenOCD in this path. So yeah, I think that's basically it from the community updates. So there's been a lot of things going on, and every day there is stuff happening. And make sure to join the Discord and participate because it's nice. There's a lot of people doing cool stuff. So if you want to follow along, you can do that there. And also we created a support channel because that was obviously needed because people were having issues. I mean it's sort of expected because you're poking at hardware and stuff usually don't go the way you expect it to when debugging on this level. Like if you have hardware that uses USB, for example, where things are a little bit more straightforward, it's usually less of a hassle. But here you're connecting to the debug port and people are using various debuggers. Yeah, all right. I should actually take this moment and inform about something. So this ST-Link clone is very popular because it's super cheap, but the problem is that it's a little bit too simple. So we've had quite a lot of problems with these. Like I've personally used it, but some people have had really big issues with it. Like had to run the script like 10 times before it started to run properly. So I think at this time we basically should ask people to avoid using this at all, like completely, because it will waste a lot of time from both us and the users if they use these kind of debuggers. So if you use this, you're basically on your own. Of course, you can ask questions, but don't expect things to work smoothly. Let's see here. I had a problem debugging code from RAM. I can't allocate ISR vector. Any experience on that? It's quite difficult to do, but luckily you can just back up your device and run from Flash. It worked for me. Yeah, I think the problem we had is that if you are in RDP1, like if it's still locked, you can execute code from RAM, but you cannot change the ISR vector, and uh, you cannot cause any interrupts to happen when you are in RDP1 and have an attached debugger. At least that's my experience. I couldn't get it to work. But I think stacksmashing, you were able to do something with interrupts if you used a certain debugger, but not with a different debugger. It was kind of strange. Or maybe if it was OpenOCD versus another debugger software. Can I continue using it, or what do you mean? I mean, of course you can continue using it, but for new users who start out and connect it and it doesn't work the first time and complain, I'm sorry, it's not us, it's this. So in order to reduce number of issues, just, yeah, it would be nice if people wouldn't use this. Yeah, I got it to work after setting lots of registers. Oh, okay, that's really interesting. Okay, cool. But yeah, so interrupts when in RDP1 is complicated, I guess. But not impossible then. Shouldn't say that it's impossible. All right, so I guess that's it for the community updates. That's, yeah, it's been a long, like a wild ride. The last few days have been really intense. Is it possible to use the Chinese ST-Links at 1.9 volts, or are they always driving the MC at 3.3? So I think the problem is that they are using 3.3 volt logic, and the STM32 runs at 1.9. So the issue is that it might not see signals properly. But since the STM32 is 3.3 volt tolerant, you won't damage the STM32 by doing so, but you might get issues. And that is also a reason why we don't want people to use the ST-Link clones, because a proper ST-Link has the VT-ref, exactly. In general, they are just buggy. Reset line is not connected, you can't connect VT-ref, and there are other issues. Yeah, exactly. Yeah, so right now I'm using an official ST-Link, like the white puck thingy, like the original one. This one. So this one has a proper VT-ref. So this pin here, it senses the voltage from the target and will use that as logic. Yeah, the voltage for the logic. Yeah, some may work, some may not, exactly. Yeah, so we're just kind of tired of them. They just cause a headache. So that's why we don't recommend them. Okay, so I can show off something I did. So this is my unit, and I'm using a hack where I'm using the USB-C connector to expose the data pins and connect those to the ST-Link. So the way this works is that I should just open up the case. Let me change the brightness a little bit. All right, this is always buggy. I don't know why it's always so buggy when you change camera settings while streaming. It works when you're preparing, and then when it's live, it's just crappy. I think actually my camera crashed. Did it actually crash? Okay, let's see here. Hello there, I've been using Olimex. Okay, and it's working fine. Not too expensive either. Yeah, Olimex usually do quality products. So that's nice. Ah, I think actually my camera crashed. That sucks. I've had so many issues with this stream today. That's too bad. The Seger J-Link Mini Edu is something like 15 euros. It's a good investment. Yeah, so I got one of those. I haven't had the time to test it yet. I will do so later. Yeah, I'm just gonna see if I can get the camera to work again. Because a stream without the camera is kind of crappy. Oh, here we go. Oh, sorry for I'm a noob at this. Sorry. So I accidentally changed the scene to something without audio. Sorry about that. So okay, just to recap. So here's a USB Type C breakout board. So you get the signals to jumper wires. And on this board, I have simply connected them magnet wires from the SWD data and clock to the USB-C connector. Yeah, sorry about the YouTube stream. I don't know how that works. I tried to use Restream, and I actually did a test stream before, and at that time it worked. But once I enabled Twitch, it sort of broke down, and I don't want to restart everything 4 times because that would be extremely annoying for you people. So I just let the Twitch stream continue, and then people will have to find the Twitch stream from the YouTube video. I'm really sorry about that, but yeah, it has. That's what I'm doing, because otherwise it would be annoying for everyone. Let's see if this works. Yeah, there we go. Ground doesn't have to be connected. No, so ground is actually ground on the whole board. So ground on the USB-C connector is the same ground as the debug ground. I mean, it's not obvious. In some hardware, you might have isolated ground for some reason. Yeah. And ideally, you want to have the voltage and reset pin exposed as well, so you get the right level shifting and so on. But yeah, I skipped out on that, and it works. But ideally, I want to have all of the signals, because there are 2 sideband signals as well. SBU, and you can actually show that USB-C pin out. So I know we talked about this on the previous stream, but I can just make a quick recap. So you have the high-speed signals, the TX and RX, and then you have the CC pin and the SBU pin. So you could use, I guess, the SBU for reset line, for example. I think that could work. All right, someone on Twitter asked me to do a walkthrough of how to actually perform the backup. So I'm gonna do it a little bit in reverse. I'm gonna start with so first of all, you have to have a debugger. In this case, I'm using a official ST-Link, so I'm gonna recommend using that. And then you saw how I connected the wires. In your case, you may connect the wires straight to the pins. So let's just assume you have done that. Then I'm just gonna let's see here. So, oh, my Windows sizes don't really match. Whatever. So I'm gonna use the restore script and restore the firmware of the unit. So what this is doing, it will flash the external and internal flash with the original images that I have already backed up. So it's doing that now. So now that it blinks, it means that it is done, and we have to power cycle. So I'm just going to power cycle, and then I press the power button, which is here, and check it out. We have the original. So let me try to emulate what a new user would do. So now I'm gonna use Docker to sort of fake that I'm a new user, and I will follow the guide. So let's follow the guide together. So let's install the prerequisites, which are these. So actually, I'm gonna use my own Docker base image because sudo and so on is not really working otherwise. Okay, so I'm just pasting whatever we have in the documentation. I guess I can make this window larger. Oh, maybe. Yeah, let's do like this. So now it's just installing the toolchain and stuff, which is not strictly needed, but it's good to have anyway, because if you do this, you probably want to develop. So now it's doing Ubuntu stuff. Takes a while. Okay. So, and now you need to install OpenOCD from my repository. That is one way to do it. So I'm just gonna copy and paste this because I'm lazy, and I know users are lazy. So if we have something copy pastable, people will copy paste it. Okay, let's see if we have OpenOCD. Yeah, we do. Perfect. So now let's clone the repository. And then we need to export a value, environment value variable, like so. So this tells the system to use OpenOCD Git that we just installed. Now that's done. We can run the scripts. Okay, sanity check works. Backup flash. So this script will extract the external encrypted flash. Oh, we got a spammer again. Let me just kick it. Oh, thanks. Okay, cool. So backup flash, and then you need to provide which debugger you're using. So in our case, it is the SD-Link. So I'm pressing enter. Make sure your Game & Watch is turned on and in the time screen. Press return when ready. Yeah, and as you can see in the video down to the right, it is. So pressing enter. It's doing stuff. It takes a while. It's normal. Oh, crap. It failed. Why did it fail? Okay, I mean, it's always the demo effect. I shouldn't do this stuff on the stream. But I really wanted to try it out live because this is probably like a user experience. So let's power cycle it and try it again. Okay. So the thing is, in this particular unit, I haven't connected the reset line. And maybe there's some jankiness going on with the wire. But yeah, I can expect people... No, I don't know why it fails. This is annoying. So I guess we have an issue with this. I wonder why the screen blinks so strangely for you. Yeah. Okay, I'm gonna blame the mod and the fact that I don't have the reset line connected. So I actually have a different unit here where I could test it, but yeah, let's make a proper video of this later on. I don't want to waste your time debugging stuff because I did that last stream. So do you have reset config none? Yeah, I think so actually. Let's check it out. Yeah. But yeah, let's not waste everyone's time trying to debug something. But I have more sympathy for users who have problems because yeah, it doesn't really always work the first time and so on. And if I was a user and I saw this, I would be sort of a little bit worried. But if I power cycle the device, you can see that it's still working. So we haven't bricked anything. Anyway, let's drop this for now and move on to whatever I wanted to do instead. Because the last stream was a sort of a disaster. I ended up wasting like 1 hour because I had a bad setup. Okay. So, what should we do today? So someone was asking me to go through how to add volume, like a mute button to the emulator. So I'm gonna do that. I think it was Eric. Anyway, let's do it. Yeah. So now I'm in the Game & Watch RetroGo repository. You can find it over here on GitHub. Save games or standby? Yeah, I was actually thinking about that as well. I will do that. I guess standby will be easy. Yeah, it's and backlight would also be nice because it's super bright. Because now I actually managed to configure the camera properly, so it doesn't look that bad. But yeah, backlight would be nice. So I guess the idea is to use this button and have some. Yeah, I mean we could integrate the menu but let's not start with that. Let's just start with something easy. Okay. Right. So let me just, yeah, let's use that as a baseline. It's an open source game. And let's just try it out without any modifications. So the way you build this project is by typing make-f makefile.nes, because we have multiple makefiles here. There is Game Boy and NES. So we can change the project structure later on, but for now this works. And then in order to flash it, you need to flash the external memory first. And this utilizes flash loader, which needs to be located and built in the parent directory, like so. Yeah, so let's try it. So, okay, this means that the debugger was not able to attach. Let's just try it again. Yep, this time it worked. So the funny thing is that even with an official ST-Link, stuff is not 100%. It's kind of sad. So what's taking time now is that it's uploading the image to RAM. That always takes a while. And then I think the script is a little bit broken, so I'm gonna do like that. Yeah, so for some reason, which I cannot really explain, it seems that sometimes, depending on the setup or debugger, if you exit OpenOCD, even if you are resuming, if you exit it, it will halt the CPU. So I'm gonna try to fix that, but not right now. So what this means is that when it blinks, the flash is programmed, and now we can program the internal flash. So let's check it out. Oh yeah, it works. It boots. Perfect. So at least we can work today. That makes me happy. In order to make it quiet, I'm just gonna do a reset halt. So now it's turned off because it makes quite a lot of sound. So I can go through the project structure a little bit. So we have been using STM32Cube.mx, which I can show you in case you're new to the stream and so on and haven't seen this program. Let me just show it to you. I'm gonna fix that. I always say that and never do. But anyway, it just informs me that I have a newer version of the program than what the project file was created with. So this is a view of the microcontroller with all the IOs and how they are configured. And then you have this view, which configures the clock tree, which is not trivial, but it lets us make sure that the timing of the LCD and audio happens at a decent refresh rate. So in this case, we're using 48 kilohertz for the audio, and we use that as sort of a main synchronization barrier. Yeah, and you press this button over here, generate code, and it will generate code. And the code it generates is, most importantly, the drivers. It will copy the drivers, and then it will generate the actual main and interrupt configuration. So there's a lot of like auto-generated code here. Okay, it's not a lot, but stuff like the system tick handler, it will tell the HAL to increase the tick. So this is like the main clock. When you say, I want to sleep for 1 millisecond, it will wait until this global variable increases and stuff like that. And then in the main file, this is all generated. It will set up the GPIOs, it will set up the peripherals and so on with the configuration that we have set in the project file. So let me see if it made some changes. Yeah, no, we can keep it like that. So most programs have a function called main, which is the starting point. But that is not really true in a microcontroller. You have something called a reset handler, which is the actual main starting point. That sets up a couple of things, and eventually you end up in your main function. So in the main function, we do some initialization and set up stuff like the memory mapped external flash and LCD driver and so on and so on. And I'm actually looking at the flash loader, but yeah, I should be looking at the RetroGo project, but it's basically the same. It is basically the same. So maybe when I press, yeah, right. Okay, so in the main function, we do some stuff. Yeah. Here's a few extra peripherals that we are initializing. Yeah, I can't English today. Sorry. Anyway, eventually we end up in this at this point, and when we have reached this, that means that everything is set up and we are ready to go. So app main is the emulator's main function. So today we're looking at the Visual Studio Code is not always good. It didn't really show me the function I was looking for. I was looking for this main file. Yeah, here we go. So this is the main file for the Nintendo emulator. And it sets things up. It starts the audio DMA transfer, which in turn generates... So this works as sort of the heartbeat in the system, because what it does is that it transmits the audio buffer DMA, the audio buffer to the actual audio hardware. And there are interrupts. In case you're not familiar with what an interrupt is, it's basically a low-level callback function. Basically, it stops whatever you're doing and does this instead. So if you're calculating pi, for example, and an interrupt occurs, then you will be interrupted. Your calculation of pi will not happen right now, and we will jump into an interrupt handler. And eventually, so the HAL, hardware abstraction layer, lets us hook in to that system and do stuff when an interrupt happens. And interrupts are they should usually be very, very short, because you don't want to spend time in an interrupt handler because you're stalling the rest of the system. You want them to be basically transparent. So what we're doing here, we are just setting state between two different states. So half full or transfer complete. And we're using these as a synchronization state. And actually, when I was reviewing this code a little bit later, I think this is wrong. I wrote this a little bit when I was a little bit unfocused, I guess. But essentially, I'm keeping track of the last state, and the intention is to wait until the state changes. But this is like written opposite, and I'm actually not updating the last DMA state. So I guess it just works because we're lucky. But essentially, we want to do stuff in this way and like this. So we want to wait until the DMA state is not the last DMA state. So we want to stall here until the transfer has changed. So let's, we can continue. So in the main function, we do all this kind of stuff. And here we start the DMA. So once the DMA transfer is running, we have these two states that keep flipping on and off. And then here's the main function for the no-friendo. We tell the emulator to basically start executing. And I think it's this one, yeah. And it does some more setup, init, insert cart, and eventually it does emulate, which is a blocking loop. So it will stay in this loop and get input, render, maybe show it on screen, generate audio for us, and then wait for the barrier. So this ensures that our frame rate is at most 60 FPS. Without this, we could run at like 200 FPS if it's something very simple, and that's not good because you want it to run at the perfect frame rate. All right, so now you know how that works. So let's take a look at the input function. How do we actually handle key inputs? So we have this function called osd_get_input, which is called by the emulator in this while loop. So here we have an abstraction function for the key inputs. So here we read all the different GPIOs. So these values will correspond to either 1 or 0 for each button. So I wonder, we don't have the power button here, but we have the pause button. So we can add the power button later. So we're limited by 32 buttons, which is fine because we want to keep it at 32 bits, right? So essentially we could add the power button here like so, and do like that. And then we can add power, and then we need a power button. So the question is, do we have the power button at all? Can check. Right, I don't think the power button has been mapped out, so we need to do that. So how do you do that? Let's check the wiki. So thankfully, stacksmashing has already done a lot of mapping for us. So let's check the wiki and go to buttons. Oh, look at this. So PA0, also known as pin number 22, is power. So let's map this up in the STM32Cube MX. So it was PA0. There we go. Should be a GPIO input. And we can also call it something. This way it will generate macros for us, so we can find it. btn underscore, should we call it PWR perhaps? Because we have btn already. Yeah, this would be good. And then we do save and generate. Takes a while. Okay, and then we go back to this one. And we can check this main.h. This is generated, I think. So we should see okay, either I did something wrong or I'm actually in the wrong project. Let me just do something. 1 second. Yeah, okay. It's kind of confusing when you have project files called the same thing. And because I have been moving stuff between repositories, I was actually in the wrong project. So just a second. And so now we're back again. And let me do the same thing one more time. We have the GPIO input, and we should right click, press this button, btn pwr. Perfect. And let's save it and generate. Oh, look at this. These two new lines, you see the green here, they represent the power button. Cool. So where were we? Right. So like so. And honestly, I don't know if it's a positive or negative logic, but let's just do like this. And increase that one. Yeah. Nice. So now we should be able to get the power buttons state as well. Perfect. So we wanted to get the pause button actually. That was the reason we started to look at this code. So let's just do that. Pause. So what is this? Ah, okay. So this is to feed input into the emulator, and this doesn't actually exist. So we shouldn't really do that. But instead we can do something else. So if we are pressing the pause button, we can, yeah, for example, just print something. It's always nice to have a print. And then we can have a static variable where we update that. Actually, we can do it like this. So essentially, if the stored value differs from the value that we're reading, we go into this if case, and then we can actually check if pause is pressed, we actually print it. And then we save the state. Yeah, this should work. So we don't want to spam the log, because otherwise this will happen every frame. So we only want the transition. So now we flash it again. It takes a little while, unfortunately. And because of the way the code is set up, we need to flash both the external and internal flash. That, yeah, should work. Takes a little while. All right, because of the stupid... I want to fix that code, but not right now. So for now, we have to do a manual OpenOCD command where we tell the debugger to resume. But yeah. Okay, here we go. So let me just make it silent. Okay, whatever. It's just annoying for me. I guess you can't hear it. Okay. Oh, the log buffer is... Wait, what just happened? Ah, there we go. Okay, here you can see that pause was pressed, which means that our code seems to work. So here we have an event, pause was pressed. Cool. Now what? What do we want when that button is pressed? Well, we can have a global variable called do we have a bool? Let's include bool. And call it audio mute. And then we can go here and say like this. So actually we don't really need this state handling or event handling, we could actually just have it updating it every time. But I wanted to write this code just to show you that, yeah, you don't want to always execute code whenever, yeah, for each frame. I don't know. So let's just do like this, or actually, so actually my memory is a little bit bad. How does bool t actually work? So you can use lowercase true and false. Right. Fancy. And then we can go to our audio stuff. And then instead of doing this, we can just we can just do like if muted, we just return. Or no, we shouldn't do that. We should write zeros to the buffer, because otherwise, if you have a sample, it will just keep playing that sample. Then it should return. Otherwise, if it's not muted, we will do this. Cool. Maybe I've inverted the logic. We'll see. It's faster to just try it. Oh, I have a build error. That doesn't. Okay. So bool t doesn't. Okay, so let's not use that then. Let's use. Hello, drones flyer. Let's just use a native word and do like so instead. Actually, this is wrong. So we want to be able to unmute as well, right? So let's do it like this. I wasn't actually thinking. So we can say like this. Yeah. So okay. So if the button is pressed, or if the button pressed state is changing state, and it's actually in the on state, then we will flip the mute state. Love the Game & Watch. Yeah, nice to hear that. Awesome. So let's try this and see if it works. So I'm just gonna do this little hack just to make the flashing work. And there it's done. Perfect. And then we flash the internal flash. Okay, so I can do like this. No. Okay, there is actually sound playing now, and when I press it, the sound is gone. And now there's sound again. Perfect. So our code works. That was nice. For once, the demo effect didn't break it. And we can actually show it in the log. Like so. And like so. So here you can see that when I pressed the pause button, it went from not muted to muted. And then I pressed it again, and it went from muted to not muted. And now it's muted again, which means that it works. Perfect. Now we can actually commit this, and I'm gonna move that over here. Let's keep everything like so. Actually, here's a little bit more better place, perhaps. So, yeah, exactly. Yeah, the demo devil. I'm not a good friend with the demo devil. There we go. Can you draw something on the screen to show mute state? Yeah, definitely, but it will require me to add some drawing code. We can do it actually in a quite fancy way, but let me just commit this. So we have, oh, right. So this is extremely annoying. For some very strange reason, the S-Link program is exporting files with Windows new lines, which bothers me. So I'm just gonna fix that. And then I guess this startup script as well. No? Okay. Okay, so let's just review. Okay, we got a few extra pins for the power. Perfect. Roam info, we don't commit. Button, yes. Main.c. Ah yeah, we got these. Oh yeah, I should fix this actually. Yeah, okay, I'm gonna fix that. So this changes the power up sequence. So D4 should be reset. So let me just fix that. It's a little bit unrelated, but I just want to make a nice commit. There we go. And right, how do you do this again? So there is a way to change the initial state of the GPIO somewhere. Let's see if I can find it. So where are generic GPIOs located? Ah, there. I was not looking. So D4, right? Just double checking with the code. And D4 should be reset. Okay. D4 should be low. Cool. Now we fix that. We press, oops, we press save and generate again. And then let's do the just to Unix again. Okay, this looks better. So pin 8 is set, but 4 is not set. Perfect. And then this one is here. Nice. Okay, so now we can add that as well. Go to main. Here we added the mute stuff, and we changed this. This is basically just, yeah, it improves it. And then here we have the actual mute. And here we have the state handling for the pause button. Cool. Let's add it. And then let's add the project file as well. So now that's done. Add mute. Cool. Let's push it. All right. So now you have a mute button. That's nice. And if you want to have an indicator for that, yes, you can do that. There are many ways to do it, but let me just show you something in the main file. So we have something called layers. This hardware supports blending multiple layers together in hardware for free, which is really cool. That means that we can have two separate frame buffers in, I think, even different resolutions that will be blended together by hardware. So you don't need to loop over each pixel to add and divide and so on, but the hardware actually does that for you. Yeah, it is. And another cool thing is that the hardware supports different pixel formats. So in the NES emulator, I'm actually using the lookup table, which means that we have 256 different colors that are indexed. So for example, when you say, I want to use color 4, you can set any color you want. And then you can also change the palette whenever you want. which is really cool. So I haven't really tried this, but I think you should be able to rotate a palette while rendering. So that's like an old school effect to be able to do lava and fire and so on for really, really cheap, because the palette is only 256 bytes, but the frame buffer is huge in comparison. So you have 256 or 320 by 240 times 2. Now let's just keep it in the number of words. So you have this many entries. So normally when you render an effect, you need to loop, you need to do some sort of operation on this many pixels. So let's say it takes 16 clock cycles per operation. Okay, that's this many. Or you pre-calculate the different table, and you just do a mem copy, which is 256. That's like quite the ratio. So it's a really, really old effect, but it's really cool, and it's basically free. So anyway, this hardware can do that, or should be able to do that. I haven't actually tried it, but so in the, let's see here, NES main NES. We get a callback from the system or from the emulator that tells us that, okay, you have a new palette, and I prepare this palette and I set it. So what I'm doing here is that the NES has 2 extra bits, which are, it tells it if it's like a sprite or background, I think. But the problem is that you cannot just have a 64 entry lookup table. So there are only 64 colors in NES, but here we kind of triple map them so that for each color in the palette, they are mapped to the index, and the index with this bit set and the index with that bit set. And it seems to work. I honestly don't know if you can have both of these bits set. Oh, a bit of a random question, but does the emulator support PAL ROMs? So I haven't tried, but as of today, it will probably just run faster. So what we need to do to support PAL ROMs is to change the DMA setting from being 60 hertz to being 50. So, but the resolution will also change. I think stacksmashing. Maybe you have tested this. I haven't actually done that, but isn't the resolution a little bit different on PAL ROMs? Because right now I'm just mem copying stuff like this. So maybe if we are lucky, the padding will be adjusted. I think actually this is a hard-coded value. Right. I ran a PAL ROM and it ran fine. Okay. Yeah, I trust you. I just don't really understand how, like, what is actually the difference between PAL and NTSC. Like, I know what it is outside of emulation. Like, it's 2 different resolutions, and NTSC is never the same color. But other than that, I don't really know how how it maps in this. NES games have, yeah, exactly. So it's a slightly different. So it's a little bit higher, 240. Yeah. So NTSC is a little bit more widescreen, I guess. Yeah. But I honestly don't know if you can see, or if this actually handles it, because our height will be sort of automatically adjusted. Because we have 240, right? So actually, let's take a look on the camera. So now it's actually a little bit bright, but I don't know. Maybe there is like a tiny black bar in the beginning and end. Or I'm actually running in PAL mode and I just don't know about it. So as you can tell, I don't know much about emulation. I've just sort of made this work. But yeah, the emulator has this defined, so it knows, it is aware of NTSC and PAL. So I think, yeah, if we just spend some time, we can make it work properly, and also sound should run at the correct time, like the correct sample rate, or like your frame refresh rate should match, because otherwise you get like a high pitch sound, and everything will sound like off tune, like off key. Yeah, but anyway, I haven't done anything with that. So going back to the key and OSD stuff. So actually, there is support in this project for an on-screen display OSD, but I haven't actually tried it. So I'm gonna open up an editor where we look at the original source code. So I'm just gonna adapt this view so I see the chat, because I have that with the tmux. Like so. Okay, now I can see the chat as well while exploring this code. So if we look at, let's see here, we are here, right? We want to look at no friendo main.c. So this is the ESP32 microcontroller integration. I mean, this is the original project that I forked, the RetroGrow fork project. Sorry. Hey, sorry, I didn't mean to take you on a tangent. If you had something else you wanted to do, yeah, no. So what I would like to do is to implement the full OSD. That would be cool. But it is an interesting question, and it opens up like it's a good segue to actually implement the OSD, because there is one. I just have never seen it, but I know there should be one. So actually, I think we can retro go if we look that up. Oh, is that actually a product? I have to look. Nah, some other day. Okay, it's supposed to look like this. Okay, let me just. Yep. So I would guess that this is the on-screen device, or OSD, the on-screen display, that we should be able to show. I just haven't integrated it at all, so we can do that. Yeah, so going back to the source. So there are some references to the OSD. So yeah. I mean, this would be really cool to have a state saving. Yeah, let's see here what they do. So here in the input, I think they check if the OSD is active. No, okay, they actually do some netplay stuff. Netplay, I don't really know what netplay is, but I can guess, and I think we don't need to support it. Yeah. So I guess this is something that we want to do. Overlay game settings menu, I guess. So here it's implemented. Okay, so this is file. The Odroid overlay implements the actual OSD, I think. It's blocking here for a key to be pressed. Yeah, I have actually not looked at this code at all. Okay, so this seems to actually be the sort of OSD main loop, or not really main loop, but render function. So where is this called? It is called there. Okay, so there are two entry points. There's the overlay game menu and overlay game settings menu. Okay, interesting. So in this case, it seems that there are two different. What is the different here. Input menu and input volume. Okay, so if you press volume, this shows up. Okay, interesting. Yeah, there is no dedicated volume button on this one. I guess if we want to differentiate between the two menus, we can find a way. Like for example, if you hold it or something for a while. That should be easy. But yeah, maybe we should try with this one just. Odroid overlay game menu. And see if we can use that. So I'm just going to be really crude and just always show the OSD menu, because that way we don't need to care about anything. Just we could also just do hold, pause, and press up. Yeah, exactly. Yeah, definitely. But I'm kind of curious about the OSD because I haven't seen it at all. As I was, it's kind of funny because this whole project, I've never actually seen it work. I just ported it and it worked. It's kind of funny. Though I guess if it's in there already, yeah, exactly. So what I did when I began porting was that I made a Linux build because I know desktop Linux a little bit. Like I'm convenient with that. I feel comfortable with that. And also, if you need to debug, it's really easy to do so. So I just did like so. And let's see if I have the elf file. Yeah. Yeah, and you see here? Here I have a Windows emulator of the same game. And it actually works. um, so the reason why I did this again was to... Alright. I forgot the buttons. It's some weird button. Already forgot what they are. Anyway, so again, the reason why I did this was to be able to debug and understand the main loop and understand how everything ties together. So I just did a really dirty SDL implementation here where I create a window and I set up the audio device and I basically just update the pixels like so. And it's really horrible. Don't look. It's probably super wrong and horrible. But anyway, it worked. And I also found some bug in some integration part that I did using address sanitizer. So in case you don't know about address sanitizer, it's an amazing tool that you should know about. It finds memory corruption bugs. I'm sure stacksmashing can explain more in detail how and why it works, but I'm just a user of it. It's it basically finds when you are writing outside of or access memory outside of static arrays, and it has a bunch of cool applications that we don't need to talk about right now. But yeah, it's awesome. Oh, interesting, JTH. It's really nice to have some people who know their stuff here on the stream. Yeah, explaining Asan might be a better. Yeah, exactly. Just ad hocing that is a little bit. Well, that's for another time. But it would be fun to make like a live stream where we fuzz some code. I don't know, maybe that's not popular to find bugs on stream, but you can definitely do that. All right, let's go back to what we were doing. Main somewhere, mainness, and then the key something, or input. All right, I'm just gonna double check if my invite still works on this thing, because apparently invite failed. Yeah, let me let me just spend a few seconds on updating that. So maybe we should take a little break, and I will be back in say 5 minutes, just a breather. So yeah, see you soon. All right, and I'm back again. I should be better at taking some breaks because those are actually needed. Just getting some fresh air in here. Cleaning the mind. All right, so we are trying to render the on-screen display overlay. So let's just call this function always and see what happens. So in this build, how is this implemented? I've actually just stubbed this out because when I ported this, I was being very lazy. So the way this project is set up is that you have this Odroid integration layer, which contains it, or is supposed to contain implementations for various hardware-specific things. And when I ported this, I just went and removed everything and implemented whatever was essential and stubbed out everything else. So right now, return 0 on everything. So let's see if we can integrate some stuff or reintegrate it. So this is the original code, and this file is like 600 lines. Wow. And how does it actually work? We can try to read the code and try to understand what it does. So again, this is the sort of entry point. It okay, so this is a menu system. So here we have, let's just check this, an ID, some sort of text, some sort of value, if it's enabled or not, and then a callback function. So this is a interesting way to do it. Like it's not strange or bad. It's just okay. This is how it works. And the update function gets to one pointer with the actual choice. And what is a choice? Let's check it out. Okay, so it's a pointer to this struct. Okay, so it's basically like this pointer, and then some sort of event. And the event can be either init, previous, next, or enter. Okay, that's interesting. So I guess there is probably an init function then. Okay, here's the init function. And it allocates the frame buffer, I think. Yeah. And it sets the font size, which I don't know how it's implemented. Let's check it out. Okay, it just sets a value. Okay, so they have this Odroid settings structure where they have some sort of key value storage, which I believe would be persistent. I don't know. Oh, they store it in JSON. Okay, interesting. How is it stored? It's stored in some sort of RAM structure, I guess. Yeah. So do they save this? Init. Commit. Okay. So they need to call this at some point, where they actually save the new settings. Okay. Interesting. So as you can tell, I'm completely new to this code base. I've just implemented the essential things. So we're exploring this together. Here is some text rendering code. So I guess this is constant kerning and so on, no fancy stuff. Oh, it saves to SD card, which is also not implemented. No. But we could adapt that and make it save to the external flash. It's just a matter of, this is an API, and we can just implement it in a different way. So that would be pretty cool. Like you state save it to the external flash and whatever. Maybe you want to take a screenshot, you can do that and save it. But yeah, none of that is implemented because you know, I was just trying to get it to run. Okay, so here's actually the code to render text. So it copies from a glyph to the buffer in the scale. Oh, interesting. Okay, and then finally it will commit the overlay buffer. So there is an overlay buffer which is allocated here. So it is as wide as the actual screen, but it's only 32 pixels high. And the reason to that is probably, I'm guessing here, so that they can write one full line of text and commit that and overwrite that on top of the frame buffer. Doing this, they don't have to keep two separate frame buffers in memory, which is kind of smart because wasting memory is bad, or maybe not bad, but if you don't have a lot of it, it's not good. So how's this implemented? They simply do a copy rect. Okay, and is it transparent? Does it handle anything of that? Well, we could. I mean, the simplest way is to just have two separate frame buffers and use the hardware to render the two frame buffers on top, but we will waste 76 kilobytes. Yeah, I don't know. Draw text line. So what does a line mean? It will pause with text color BG. I don't immediately see the difference. So it steps. Yeah. So width is probably the intended width of the rectangle that you're rendering. And a glyph is the a glyph of the character. So here's a font, and this looks kind of compact. So it's a 8x8, very small font. All right. And then for each line in the font, and then for each column of the glyph. So I mean, this copies one full glyph, and this goes through the whole buffer. So how does it change the? How does it select character? Well, there should be a glyph here, right? So here it's using the I variable. Okay. So basically, it uses the space glyph if we are out of bounds. Otherwise, it uses the character that you're at in your text. So for example, if it's OX4041, capital A, it will use this table, go to 41, which is a capital A, and it will use this as a glyph. That's how it works. Okay, now we understand the code. Interesting. So what is this then? Why do you need this? Draw text. Okay, now I see. So this is a helper function for this. So it sets up and goes through the text and makes sure to increment the y position with the height. Yeah. Now I understand. So whenever you want to write 3 lines of text, you call this function with your full text, and it will take care of it. Cool. Okay, so now we know how that works. And draw rect is probably just drawing a rectangle with the color. Yeah, so it just okay, interesting. So it fills the overlay buffer with the color, and then it just copies it. Okay. Draw fill rect. Oh, right. Sorry. So this is actually just drawing the borders. And this one is fiddling it. Right. Draw battery. Okay. So there's a lot of hard-coded GUI values. So I wonder, what is the resolution of... It's a little bit hard to know from these... from this code. Like, there's a lot of hard-coded values around here, but do we actually know what the size is of this device? Okay, I mean, this is quite a lot of work to get working, but I don't know. I mean, we could do it, or we can just put it on the to-do list and say, yeah, at some point in the future, we someone should take this file and adapt it, because I think that might be a little bit too much work to do on stream, and it might be a little bit boring. But yeah, essentially what you need to do is to, yeah, copy this font code and adapt the sort of GUI drawing code. For example, all of these hard-coded sizes and values, make sure that they fit. Okay, actually they use the same resolution as we do, so I guess I could just copy it. Okay, but honestly, I'm not really feeling it right now. And unless people are asking me to do it, like, yeah, come on, do it. Okay, thanks. Yeah, some other time, I guess. Yeah, okay. So let's get back to the code, and let's try to implement the power button. So this might actually be a good thing to do on stream. Yeah, let's do power. So let's go to the main NES. I don't. I'm in the wrong project. So NES main, or main NES. Cool. So here we implemented the pause button. So let's implement the power button. So wait a second. Where does this come from? Ah, okay. So we forgot to add this power, like so. So actually this code can be removed, and we can include, actually we do that here already. Yeah. Let's see if it builds. Yeah, it builds. And let's go back to the H file and use this define, and use it over here. Power pressed. Yeah. So before we start implementing some power code, let's just check it if we can detect it. So right. So again, I'm flashing the external flash. and it's done. And I'm muting it, and I'm gonna attach the debugger. And I'm pressing the button once. And we can see here that button was pressed and released. Oh, here's something weird happened. So I guess I messed up. Something strange happened here. So power pressed. So I pressed it twice. So yeah, isn't B power? Oh yeah, you're right actually. Yeah, I didn't think. I was expecting it to be Boolean, but it's all right. It's because we're actually looking at the value. You are completely correct. Yeah, so I guess I shouldn't really do like this. Let's do like that. So I want the value to be 0 or 1 basically. So I pressed it twice. Okay, pressing it one more time. So I don't get the power pressed 0 to 1 for some reason. I'm probably just being stupid. I just don't see it. So because okay, actually let's break. So now when I press it, we get in here. Okay, fine. I'm just gonna keep holding it. Right. I'm not really sure what I was thinking here. This is like whiteboard coding. It's like it's a really simple problem, but I just cannot use my brain right now. So I mean, I just want to keep a state for pressed if that differs from the actual value. All right, I should actually check this value. right? So and then we can keep it like, because negating will be, yeah, right. Okay, now I changed too much. I have to flash the external flash again. Okay, so I'm pressing the button, holding it down, and then we see that power pressed 0 to 1. Okay, cool. And I'm releasing the button, and we see that we don't see that it. Oh, right, because I don't print it. I'm so stupid. This should be here. Right. This should be right. Yeah, no, I don't envy people who have to do whiteboard coding for interviews. That is just horrible. Oh, look at this. It's broken. Okay, again. Let's press and hold and then release it. And now we can print it. Yeah, okay. 0 to 1 and then 512 to 0. Okay, but this is fine. This makes sense. So, when we press power, what do we want to do? Well, we want to shut down the system. How do you actually do that? I think the inner if statement is redundant. Yeah, you are right. But this is basically pressed. Right. So here we see that, okay, it toggled, and here we see that, yes, it was actually indeed pressed. And we can do like this. Yeah, okay, now I get it. Yeah, definitely. So, again, how do you turn off the STM32? I don't actually know. I know that you can configure. So let's keep this code there and just move a little bit ahead of ourselves, and actually implement how to wake up. Because not being able to going to sleep and not being able to wake up, that is not really fun. So we have this power button, which was here, right? And as you can see, maybe it's hard to see on the stream, but there is actually power wake up 1. You see there? Power wake up 1. And let's use that one instead. And then we need to sort of dynamically, while running, change. So we need to toggle between the two functionalities, either GPIO or a wake up button. So let's just cheat a little bit and say now we want it to be a wake up button and see what the SDK generates for us, or the tool. So we're saving, And let's check the diff. So it changed a little bit in main. Okay. Configure GPIO pin. And oh, nice. No, it removed that. Okay. Did it change something else? Da, 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 no. So I guess the power on functionality is a hardwired feature that you cannot enable or disable, which also means that we don't need to worry about it. So let's move back one step. Input. Just manually revert, see what happens. Okay, so we're back again, and everything should build. Let's just verify that it builds. Yes. Okay, so what we want to do now is we want to enter deep sleep. So I don't actually know how to do that. So we have to look at the reference manual. So there's a likelihood there that there is a HAL function for that. So if we just search for sleep and look at some reasonable file, maybe the HAL file, we can probably find something. Power. Yeah, look at this. Perfect. Call HAL power enter sleep mode function. Enter the current core in sleep. Wake up from sleep, either from an interrupt. Yeah. Okay. So I guess we should call this one as well. Enable wake up pin, because the power button is a wake up pin. I am here. I have to sleep also. 1 a.m. here. Oh, yeah. Yeah. I'm sorry for the time zone difference. It is what it is. But thanks for joining. See you next time. And see you around in the chat. Okay, so I guess we need to call this one first. And then, good morning. Yeah, nice. Is it American time, I guess? So, yeah. Enter sleep mode. Yeah, that's right. Oh, yeah. So there's a stop mode as well. So what's the difference between sleep, stop, and standby? Yeah. All right. When we're entering sleep mode, we maybe we need to stop the DMA job before we go into sleep, because otherwise, when the DMA job is complete, it will generate an interrupt. Yeah, this is kind of interesting. So let's read a little bit about sleep. What is sleep? Oh, operating mode. Wow, okay. Ooh, so run is the highest level, it seems, where everything is on. Then we have something called sleep, which seems to be a light sleep. It's like REM. And then we have the stop sleep, stop mode, where things seem to be actually turned off. Like this, the system clock is turned off. Yeah. Right. So it seems actually that when you're in sleep mode, you can do quite a lot. It's only the CPU that is sleeping. But I guess we want to go into deep sleep, like actual standby. Okay, entry. That is how to enter again. Okay. So I guess ideally we want this. Oh, right. So I don't know. It seems like you might want standby. Yeah, I think so too. But I'm just thinking if RTC is something that we care about. Like the actual product, the game and watch has a clock, like an actual timekeeping clock that runs. And we haven't each actually enabled it. Maybe we should do that as well. But yeah, wake up pin rising or falling edge. And wake up pin is, I'm guessing that the power pin is one of those pins. This is PA0. So I guess we can look at the data sheet, which is not the same thing as a reference manual. PA0. Can it tell me the matrix? Yes. Okay. Okay. Wow, that's a lot of wake up 0. Okay, here you can see additional functions. Wake up 0. Yeah. Okay, so you may have multiple wake up pins. The RTC can run something. The RTC can still run while you're in standby. Wow, that's impressive actually, because standby is really low power, I guess. Yeah, I mean, let's just try it, see what happens. The worst thing that happens is that we get stuck in standby mode. So let's just call that. Right, and we only have a single core, so we don't need to worry. So power button pressed, and then I'll delay 500 milliseconds, and then let's call it. Because one thing you really don't want to end up in is sort of a standby loop that immediately when you boot, it will enter standby mode, because that is a pain to recover from, because you need to attach the debugger at the right time, and you know that's why I put a delay here. So let's do that. Make, and then flash it again. Oh, I didn't realize, Yuxan, that it was you. Thanks a lot for the PR that you made. Very nice. Yeah, let's see here. Resume. And sorry if I pronounce your name incorrectly. Yeah. Okay, here we go. Okay, it boots. So let's press the power button. Oh, check it out. Turn off. And let's see if I can debug it. I actually can debug it. Or no, it's sort of in a weird state. Yeah. Okay, so now it's in this sort of horrible state where it's sleeping and you cannot debug it, which is what we want. We want it to sleep. So let's try press the button again. It doesn't wake up. English speaking people almost always get my name pronounced right. Okay, cool. Is it like Yoksan or Yoksan? So I think I need to power cycle the device because it's stuck in deep sleep. And yeah, thankfully it actually woke up. Actually, the mute button is really useful. So thanks for pushing me to do that. Okay, so now we know that we can enter standby, but we need to be able to exit standby. So I think we need to do this one, enable wake up pin. So let's do that and check if we need some arguments. Yeah, we need some sort of polarity. Pin 1 high. The second way. Okay, Yoksan. All right, cool. Yeah, so the wake up pin. So I guess here. Right. So this means that it's active low. When the pin is low, it is pressed. So we want to use this one. But I'm confused about the index because here it's called pin 1, but in the datasheet it was called wake up 0. So I don't know. Maybe we need to configure what 1 means. So let's just do that. But maybe we need to configure the actual pin as well. Wake up pin configuration. Okay, this sounds relevant. Wake up pin is used to wake up the system from standby mode. Okay. Okay. Well, what confuses me is the indexes don't match. Like here it starts on 1, but it starts on 0 in the documentation. But yeah, I guess we can just try it and see if it works. It's not the end of the world if it doesn't. And yeah, let's press it, see what happens. Okay, it went down. And it started again. But it's in a sort of broken state. Okay. So, interesting. So a few things. We should turn off the audio because otherwise we get like a annoying sound here. I guess we can abort the DMA job. So we have this one. Let's see if there is a function for stop. I think there is. DMA stop. I don't think it takes any more arguments. No, exactly. So this is cool. This makes the sound stop, and then we still do the delay. This seems to work. It actually works. So pin 1 is the power button. But then when we get back, let's do like this. Let's see if we actually end up here. Because I noticed that stuff was like restarting, but it should have delayed a little bit more. It didn't really make sense what we saw. Okay, let me reset. Yeah, and once we got this, I'm gonna measure the current to see that we're actually not drawing. There's many things to consider when entering standby mode, such as peripheral state. Things like the LCD controller stop working. Also, the CPU resets when waking up. Okay, that's very good information. Oops. There we go. Okay, so now it seems the display got sad. Okay. Oh, now it seems to work. Why didn't it work before? Okay. So now it seems like we are not able to enter sleep state again. Interesting. So after entering standby and waking up with the button, we are in a strange state, it seems. So is there a way to sort of perform a full reboot when we wake up from reset or standby? Do we have a part number on the LCD module? No, not that I know of. Or actually, there is a number, but if you Google it, oh, you do. Okay, because I couldn't find any information about it. Do you need to disable the wake up pin? Oh, thank you. Wow, that I didn't think about that. Because there is actually the enable wake up pin and disable wake up pin. So, question is, where should I call this? Like, is this ever gonna happen? Probably not, right? So I probably need to do this in main, in the literally main function. Like, let's do that here and use this pin. Actually, maybe it should actually be happening before the GPIO init. So let's put it here. Yeah, let's try this. But it's proprietary Innolux, custom made for Nintendo. Okay. That explains why we cannot find anything when we Google it, right? Yeah. Oh, you're right, Yoxan. That I think we have only sniffed the on sequence. Maybe there is a off sequence. Is the LCD backlight still on when the STM is asleep? No. Because actually, I'm kind of curious now. How does that work? Like, sleep is curious to me. I've never fully understood how sleep works. Like, what happens with the GPIO pins? Because no, I do not. I don't do anything. Like, I literally do. If you check the stream, I do this. I enter standby mode and I start an infinite NOP. So I don't do anything. And when I wake up again, I am not running this code. I'm actually doing something else. So I guess we end up in the reset handler and boot like normally, except that there are some internal states in the MCU that's different. As we turn off the display via PD1, I don't think we need it. Right. Yeah, I guess so. I'm just curious that I was actually under the impression that the GPIO states would stay the way they are when you enter sleep mode, but apparently that's not the case. But yeah, let's try this. And flash. The driver module will need to be turned off if we want to save battery, particularly because, yeah, okay. So I guess we can, obviously we can improve on this. So I'm pressing the button now, press, and now it's off, and I'm pressing it again, and it turns on, and the sound works. So let me try to enter deep sleep again. Yeah, it actually works. So yeah, this change was definitely needed. Oh, this time the display didn't turn on properly. So I guess there is some funkiness in the command sequence that sometimes it works, sometimes it doesn't. There is some flakiness. So now it's in deep sleep mode, and let me check the current. So I'm gonna grab my multimeter. Just a second. Right, let me try to move the camera so you can see what I'm doing. It's a little bit cramped here. This is really ad hoc, but let's hope it works. Like, well, let's stay. It's gonna fall any second. Okay, it seems to actually stay. Cool. Yeah. So multimeter, and then I'm gonna move around a little bit. No, sorry, it didn't stay. I'm gonna need a few minutes to set up, so I'm just gonna, yeah, I'll be back in 5 minutes. There we go. Okay, so now I have moved the camera so we can do some stuff together. So I'm gonna move the unit so we have it here, and I will be using a cable like this. So this is the 5-volt cable, and we will use that like so, because we're measuring current going through. And then we have this one, black one. This one has to come from our 5-volt source. Oh. Okay, cool. So I'm putting this in milliamp, and I will connect it. So let's see if it blows up. Okay, it turns on. Oh, of course, I reversed the polarity. So let's do like that instead. So now we have positive 130 milliamps. Wow, that's a lot. And let's mute. Okay, you see, the sound actually does quite, it's like 15 milliamps or something. 12-ish. All right, cool, cool, cool. Well, now we're measuring current, so I'm gonna press the power button. I have no idea what to expect. Oh, check it out! It actually works. That's really cool. So without any sort of effort, we're already at below 2 milliamps at sleep. And this is measuring the USB 5-volt input. You could implement wait for interrupt while the emulator sleeps. Yeah. So how does that work? Because I almost never write this code from scratch. So I'm gonna change my screen to the code again. Yep, there we go. I mean, while it waits for vsync. Oh yeah, okay. Yeah, I get it. Of course. So instead of our nop, which is somewhere, why am I blind? Yeah, here, right. So instead of doing this, we do the wait for interrupt. But we need some sort of interrupt, right? And the interrupt is every millisecond because we have the system clock. So yeah, let's try it out. Thanks for the suggestion. I've done some low power stuff before. I was working on a Nordic RF NRF52 device, which was really interesting because it was a wearable device paired with a CR, some kind of battery, the flat coin cell batteries, and it was using Bluetooth and still able to get like 2 years of battery life. And I can recommend using the NRF power profiler. It was really, really nice tool. So you get a really nice graph for the power consumption. Because in deep sleep, that chip uses 1 microamp. Like we're at 1 milliamp here, but that used 1 microamp. That's basically nothing. All right, let's see what happens. All right, it failed. Oh, right, because it's off. I forgot. So there we go. That 1 milliamp while asleep means the device can go on sleep for about 500 hours. Yeah, but I don't like it. Like that's way too much. Like 1 milliamp for just sleeping. That's crazy. Yeah. Okay, here we go. And flash. So we had like 120, right? 130. Okay. So it unfortunately didn't make a big difference. And I believe, honestly, the CPU is probably what takes least amount of power. The backlight is probably really hungry and so on. Yeah. But thanks anyway for the suggestion. This makes sense to do this instead of that. 1 milliamp isn't much for sleeping. Well, I mean, it's all about context. Because if you're doing like a wearable Bluetooth device, you want 1 microamp, which is 1,000 times less. But yeah, sure. The CPU might be waking up early due to other causes. Yeah, but if the CPU wakes up, shouldn't we get stuck in staying waking up? Like if the reset handler is called and we enter the main function, shouldn't we see the screen turn on? Yeah, I think what we have now is good enough for a commit. Um, um, during wait for interrupt. Oh yeah. Oh yeah. So the interrupts that I know of is the SysTick for the millisecond timer and the DMA transfer states, which is what I care about. Um, yeah, but there are probably other interrupts being fired to the right and the left. Is there any way to see? Do you know of any way where I can check DMAs that have been handled? Like in the system, what's it called again? The reset startup script. Yeah. So here is the big list of all the interrupt handlers, right? And all of these are either implemented or not implemented. And if they are not implemented, they have this weak set, so it will be set to the default handler, right? Oh, sorry. There we go. Okay. So again, the startup file contains this list or array of interrupt handlers. And if you have not implemented an interrupt handler, it will be set to the default handler. So what we could do is to debug. Let's halt it and debug and break in the default handler. Right. And okay, this is good because the default handler is usually just a while loop. Yeah, it's an infinite loop. So this is how the default handler is implemented. Usually, this is a good thing because if you end up using or triggering an interrupt that you're not handling, you should be aware of that. And this is a very good way of making someone aware of it. Because when you see this, okay, your system basically crashed. So that means that, yeah, we don't have any unknown handlers. That's good. So I guess what we can do is to actually print this. How do you do that? You can do like this, and just so what I'm doing here is I'm printing with x/a. A means annotate, I think. So it prints the address or the value, and if you have a symbol on that address. And in this case, we start here by the reset handler, which is implemented. So that's why we can see it. Then we have the non-maskable interrupt handler, NMI, which I'm curious how it's handled. So we can actually disassemble the NMI handler. And here we can see, okay, it's actually doing something. Is this the same as default handler? No. So the default handler, it's just one instruction where it calls itself over and over and over again. But the NMI handler is actually implemented. So using list, I can ask GDB to show me the code. But I wish it could show me the file name where it found this code. It's probably possible, but I'm not that good at GDB. If anyone in the chat knows how to do that, please let me know because I'm really curious. So what I want to do is I want a command that shows me the source code, but also where I can find this. So I mean, I can search for it. And okay, luckily it was easy to find, but sometimes it's not. So okay, this means that we have a user code here where we can implement our handler. I use grep for finding function. Yeah, I just did as well. But it would be really cool if list could tell me like verbose, just tell me where did you find it. It was really nice. So sometimes I just copy some unique code and search for it and find it. But I really don't like that style. It feels really hacky. But it is what it is. So anyway, we can. What were we doing? We were looking at the handlers. Hard fault handler, bus fault, and so on. These are all like when you so-called crash. What does that actually mean? Well, it's usually that you get one of these were triggered for some reason. Yeah. Right, so this is the default handler. Yeah, I also wish I knew how to do that from GDB. Yeah, because I tried reading the docs. I actually tried, but I couldn't figure it out. Okay, so here we have the DMA1 stream 0 handler, and this is for the audio. And that is definitely being used. So we can just illustrate that. Yep, as you can see, it is being called. Cool. Um, let's continue the list. Okay, so everything is actually the default handler. Okay, there's the Octospy handler as well. Let's actually break. I'm bad at spelling. Info line. Oh, really? Oh, thank you. You saved me so much time. Thank you very much. I will remember this. Perfect. Awesome. That made me really happy. Okay. Um, okay, it seems that interrupt is not being called. Mm. So I guess we're not actually hitting any, because this is the default handler, and we've already tried out, set a breakpoint in there, and we do not end up there. So we have the systic, and we have the pending service handler, I assume that is. Oh yeah, that's how I do it. I completely forgot. Yeah, so thanks again. That was really helpful. And we have the debug one. Okay. So systic, obviously we're gonna have a, yeah, this one comes each millisecond. Um, we have the debug mon. Probably no, that doesn't happen, which is expected. And then the usage, these are the fault handlers, and then we have the non-maskable interrupt handler. So no, I actually feel confident in saying that no, we don't have any interrupts that are firing, except for the DMA and millisecond systic. So now we know that. That was interesting. And now you also know how to check it in case you didn't. Okay, I think that's enough low power for today. I mean, we got down to, let's just show it on the camera. Like when it's muted, 109. Okay, cool. And let's start the game. All right, I need to continue. Here we go. Yeah. Seems like most of the current consumption comes from sources other than. Yeah, exactly, exactly. So again, I'm halting the CPU. Now it's halted, and you can see 108. And if I continue, we reach 122. So that is like 14 milliamps for the CPU, I guess. And now I press the button. Boop. And we go down to. Oh, this is a little bit higher than before. For some reason, it's at 6. I don't understand. It could also be this not so trusty multimeter for 20 bucks or something. Um, let's turn it on again. Okay, it seems at least consistent. Let's power cycle it. Oh, it's gonna blow. There we go. Okay, one more time. And I press the button. And now it's at 1.3. Okay, so it seems that after. Oh, you know what it is? If you debug, you enable the debug block. And if you do that, it uses more current. That's at least my theory. Looking suspiciously at the backlight consumption. Yeah, okay, yeah. Honeylab measured it, but I don't have the links. Okay. Actually, Tim also measured it. I can post it in the chat, I guess. 1 second. Um, yeah. Okay, I'm gonna post some spam in the chat. Let's just, yeah, here we go. Burp. Oh, I got rate limited. So annoying. Yeah, it makes sense. Anyway, so I haven't measured this. These measurements come from our friend Tim, who's been doing some really cool stuff as well. Yeah. Okay. So actually, in order for this stream to not become boring, maybe it's time to stop it here because we've done some interesting stuff today. Just to recap, we did some community updates and we added the mute button, and then we added the off button, and we're actually able to wake up from the off mode, and the power consumptions look good. Like we're below 2 milliamps, so that's pretty cool. Standby will be awesome. Yeah, so I will commit this, and hopefully this commit can be sort of yeah. Now what will I play through first? Yeah, yeah, it's up to you. Yeah. So there was some glitchiness when we turn it on again. So if the display doesn't turn on properly, just turn it off and on again, and it should work. But actually, now that I tested, it looks good. So yeah, power down is awesome. I can now stop unplugging the battery to save it. Yeah. Okay. So let me just finish this up. I want this one. I want that one. I don't want that. Can clean that file up a little bit. Yeah, let's remove that because that's actually in the other file as well. So we have that here. And then in the main file, did we do anything? Oh yeah. So this one was really important. And then in the main function, we keep track of the power. We changed the knob to the wait for interrupt to save some power. And then here is the power off handling. Cool. So let's add that too. And commit. Okay, so power button handling and push. Okay, so thank you everyone for joining and see you next time. So it's been really fun. And I will definitely remember that trick, info line in GDB. That was extremely helpful. Nickname 77, if you want. I upload the stream to YouTube, so you can watch that later. So perfect. Yeah, and thanks for the feedback. And if you want to suggest anything that you want me to work on, feel free to do so. Just send me a message on Twitter or on Discord, and I will keep it in mind. Of course, I can't promise anything, but I will try. So, yeah. All right. Cool. Thanks, everyone. I'll be closing it.